Awesome. So I'm Chris Harrop. I work for the Cooperative Institute for Research and Environmental Sciences at the University of Colorado, and I work within the High Performance Computing Group at the NOAA Global Systems Laboratory. Just real quick, I just wanted to acknowledge the funders of this work, the NOAA Software Engineering for Novel Architectures program, and I also wanted to say thanks to our collaborators, Department of Energy Exascale Computing Project, and also at Parallel Works. They've been extremely helpful, and this collaboration has been really great. So just to start off, NOAA has this numerical weather prediction grand challenge. What we want to do is, we're looking towards exascale and what we can do with exascale. And the grand challenge is running a global 3-kilometer cloud resolving model. And ideally, we'd like to do large ensembles of this and build digital twins that we can use to ask what if types of questions. And this requires a huge amount of computational power. And in order to sort of achieve this goal, we're looking to branch out into machine learning to replace some of the really expensive calculations with inference models instead of calculating them using our standard parameterizations. And this also offers an opportunity for increased fidelity in representation of physical processes that are happening in the atmosphere and the ocean. And of course, looking into new programming models and methods. And when we're doing this work, the High Performance Computing Group, of course, is looking forward in time. And for a while now, we've been in sort of a diversification disruption. And this is both a good thing and a bad thing. It's good because there's opportunities. It's bad because it's really challenging. And what we have is we have a multitude of vendors offering a multitude of different types of hardware, specialized hardware, everything from new processors to things like non-volatile RAM. Quantum computing's coming on, getting more and more viable. And then we also have a diversification of computing environments. We have on-premises systems, each with their own individual characteristics, and we have multiple cloud vendors and cloud environments with different characteristics. And of course, it's not just a question of learning how to use all of these individual tools, but there's also the problem that there's a non-uniform distribution of all of these different things across the different locations and places. So our workflows are not equipped to deal with this. And what we've embarked on is a project to build what I was calling just diversified distributed workflows, but I guess I should really use the word federated workflows to enable numerical weather prediction, high performance computing research. So we want to be able to have researchers who are working on trying to understand how to apply advances in high performance computing to the numerical weather prediction space, be able to sit on their laptop and farm out all of the different portions of the weather simulation, for example, to all of the different resources that are most suitable for that particular component. Right now, so let me just say that we are very, very new to both Globus Compute and Parcel. So listening to all these presentations, I am just kind of blown away by the possibilities that I've seen so far. So some of this might look pretty crude to a lot of the attendees at this workshop, but what we've done so far is we've adopted Parcel for handling the orchestration of the workflows and Globus Compute for doing the federated access to distributed resources. And because we have a strong need for running very big computational fluid dynamics simulations on large numbers of nodes, big MPI jobs, we really need MPI. And so we solved this problem with Flux currently. So what we do is we have a workflow endpoint sitting on a login node on our HPC resource, or potentially an instance in the cloud that's running a Globus Compute endpoint. And then we We haven't actually done this yet, but we're planning to have that invoke a parcel program, which then acquires the compute resources with the Flux executor, and then schedules MPI jobs as the dependencies become satisfied inside the Flux, the resources that Flux is managing. And so the idea, of course, is to have multiple of these things running across geographically distributed systems with the function as a service model and fire and forget for reliability, and everything will just be wonderful. We're not quite there yet, so we've got a lot of work to do. But some outstanding questions we still have are, for one thing, we've always expressed our workflows as XML or YAML, as configurations in the past, but now we have the opportunity to do something that's a lot more advanced and powerful. So should we keep using configurations to define our workflows and then generate Python parcel code to run them? We're not sure. Also, how do we monitor and steer the workflows? If a workflow is a running Python program, how do you interrogate it and control it? Back up the workflow, rerun things, and so on. And how do we measure performance and optimize the performance of the workflow? The other thing we're not sure of, which Yadu may have made some significant progress for us on, is how to deal with advanced MPI plus X requirements, core and socket affinity, special custom MPI vendor-specific settings that are needed. We also need NPMD launching for coupled models. Sometimes we need to launch multiple executables in the same MPI exec. And sometimes we need customized non-uniform layouts of MPI tasks on the system.
Chris, it's about time.
Okay. All right. So anyway, we're looking at how to deal with data, how to deal with complex mixture of HPC and high throughput tasks. We don't know what the best practices for designing parcel applications is, and how to deal with testing infrastructure as we develop. So I'm just gonna kind of leave this slide up and take questions at this point.
All right, we have time for one, maybe two questions. Have any questions in the audience here? How about on Zoom?
So I'm curious about your NPMD use case for the MPI. When you deploy those models, how frequently do you anticipate the kind of allocation of resources between the two programs to change? Or every time you run it, is it always kind of the same function call?
I think once the modelers have figured out how to balance the resources between the two different applications, and so that the performance matches, and they are, when the coupling exchanges data to like the ocean might have a completely different time step than the atmosphere. Once they settle on that, it's usually pretty static. Okay. But as the codes do change over time, it doesn't change quickly.
All right. Okay, that's really fascinating, and thanks for kind of walking through that. I mean, I also have strong opinions about the YAML versus Python, but yeah, maybe we can talk out of band so it's not my voice coming from the ceiling for everybody to hear.
I would love more discussion. I'm really looking forward to connecting with more of you folks.
Sure thing. Awesome.
Thank you so much, Chris. Well done.